Until now, we learned about analogous electronics. Analogous means that typical values for our parts can be chosen from infinitely many. Analogous devices create a series of problems with reparability.
Digital circuits are characterized by greater resistance to problems where the number of possible values is limited. Thanks to this, it is easier to achieve better repeatability of digital systems than analog ones. Bits and words. The logic state of one element is called a bit. At this point, our element can take only two states, high and low, because it has only one input and one output. However, devices often have more inputs and more outputs. This means they can take much more states. And what should you do then? Any number of bits can be called a word and can be used to save information in a binary system. Each bit has a corresponding weight assigned to it. Here, you can see 4 different combinations of output states that can be saved as binary words. On a daily basis, you use decimal system with 10 digits, from 0 to 9. Every number is built from these digits. For example, if you want to write information with number 103, you use 3 digits. But there are 1,000 combinations because on each of these places can be one of 10 digits. Digital circuits use only 0 and 1. At first, it seems that you cannot write this information with only 2 digits. You can only construct 101 and 110. However, with 2 digits you have only 8 possibilities. So there are too few digits to write this information. In order to convert this number into a binary word, you need to understand how to interpret binary numbers. The youngest bit is at the right and its value is 2 to the power of 0. The power increases by 1 with each position to the left. So, the value of the first bit is 1, the value of the second bit is 2, the value of the third bit is 4, value of the fourth bit is 8, and so on. To get a given number, you need to multiply value of each bit by 0 or 1 and add values from each position. So, in this example, from the first bit we've got 1, from the second 2, from the third 4, from the fourth 0, from the fifth 0, from the sixth 32, and from the seventh 64, which gives us 103. 8th bit must be 0 because 2 to the power of 7 gives you 128, which is more than 103. Let's do another example. Here we've got only 3 ones on 4th, 5th and 8th bit. So, here 2 to the power of 3 gives 8 plus 2 to the power of 4 gives 16 plus 2 to the power of 7 gives 128, which altogether give us 152. In order to convert a decimal number into a binary number, you need to divide your number by 2 and write down the remainder. So, with our previous example, 152 divided by 2 gives you 76 and your remainder is 0. 76 divided by 2 is 38 and the remainder is 0. 38 divided by 2 is 19 and your remainder is still 0. 19 divided by 2 gives you 9 and remainder equal to 1. 9 divided by 2 is 4 with remainder 1. 4 divided by 2 is 2 with remainder 0. 2 divided by 2 is 1 with remainder 0. And 1 divided by 2 is 0 with remainder 1. In order to write down the binary number, you need to go up. So, your binary number is 1, 0, 0, 1, 1, 0, 0, 0. Two-state systems are described using Boolean algebra. The most basic operations in these systems are logical product, logical sum, and negation. Results of these operations may be easily presented in form of tables called truth tables. They consist of information on the status of the output depending on the logical states of inputs. Systems performing these operations are called logic gates and they are available in form of integrated circuits. AND gate performs an operation called conjunction, which is a simple multiplication. Output is true only when all of the inputs are true. OR gate performs an operation called alternative, which is a simple sum. Output is true when at least one of the inputs is true. NOT gate performs an operation called negation, and it changes values from true to false and vice versa. It is also worth mentioning that there are more advanced gates that utilize basic logical operations. You have negative OR and negative AND gates, which are negations of OR and AND gates. Exclusive OR is a disjunctive alternative, and exclusive negative OR is exclusive OR gate's negation. There are also other, more advanced logic circuits, which are multiplexers and demultiplexers. Multiplexers have many inputs and one output, while demultiplexers have only one input and many outputs. Both have address lines which are required to differentiate data input. You can send a batch of data on one line and multiplexer will select the input, giving data a corresponding address, while demultiplexer will transmit this data to a specific output. Previously mentioned logic circuits are combinational systems, which means that their output state depends only on logic state of the inputs. However, there are also more complex logic systems in which output state depends not only on the logic states of the inputs, but also on the internal state of the system. Such systems are called triggers, and they can be built basing on logic gates. They are used to memorize current state, and they often have an additional input to synchronize changes with the clock signal.
We can do basic logic system on our own, performing specified logic operations. However, when making more complex system, using and processing many inputs, it is certain that we'll use too many logic gates, and it is worth optimizing. The basic optimizing technique is called KARNAUGH method. Later, we'll learn how to create KARNAUGH table, but first of all, we have to know how to write function equation from this table. In logic, if we want to present a value which is true, we just write its symbol. As if we want to present value that is false, we write the negation. So this means the true A and this means the false A. So if you have two groups of ones here, this group of ones depends only on A when it's false, because it doesn't matter whether B or C are true or false. Here we will have only ones. So this group can be represented as A false, and this group depends only on B and C. Doesn't matter whether A is 0 or 1, here we have also 1 and 1. So this group can be represented as no B and no C. We have to do logic device performing specified operation. In this device, we have three inputs represented in rows and columns. Rows and columns in KARNAUGH method are represented with a gray code. That means that two subsequent numbers differ only in one position. Each field of a KARNAUGH board is filled with a number representing logical state on the output with a given input values. So let's suppose we have to make our logical device. Our logical device has 3 inputs. Each row shows the different combination of states on an input. 0 means negative and 1 means positive. The output value of our device is a logical state based on inputs of different combination of inputs. Now we can convert the value of inputs into normally numbers. So this means the 0 combination. This is the first, the second, the third, the fourth, the fifth, the sixth, and the 7th combination. 7th means the binary number of this is equal to 7. Now we have to draw the Carnot table with 8 fields, so 8 different output states. We have 3 inputs, A, B, and C, put it in a rows and in a column with a gray code. Now we put the value in each field. So, for example, 0, 0, 0 means 0, and 0, 1, 0 means 2. The same as in the previous example, when we have those inputs on the left side and output on the right side. Now we put the output values in all fields. This mathematical equation shows the positive state of our inputs of our device in every combination of inputs. So for example, negative A, B and negative C means that position. Negative A, B and C is that position. But we can also group those ones into bigger groups than only one. So for example, this is a group of 2, and this is also a group of 2. Now, after grouping all those ones, we can write another mathematical equation representing our logical state. And it is much shorter and easier than the previous one. Negative A and B means those two ones, and B and C are those two ones. And this is quicker and easier to cope with logical devices using optimized functions. Now, from our equations, we can build a logical system based on gates AND, like this, and OR, which is here. Now let's practice more on other examples. Let's suppose that our device, logic device, has only 2 inputs, A and B. But the state on the output when A and B are negative is not 0 and not 1. It means there isn't such a state in our device, so we can assume that it's 1 or 0, and it doesn't matter. Now we can draw the Carnot table from our function. We see that it's only one positive state in this field, so our function is negative A and B. But let's suppose that this unknown state is also positive. So now we can group those two ones, and our function will be only negative A. This is much simpler. On logic gates, it is also visible that assuming the unknown state is equal to 1 is much easier because we have less number of logic gates. Now let's move to the more complex example. These are logical values of a more complex example. We have 4 inputs, A, B, C, D, and 1 output. Each combination represents one output value. There are 16 combinations, so let's put decimal numbers next to binary ones. So it's 0, the first state, second, third, and so on. This is blind Carnot board for our logical device. For beginners, it is easier to put all those numbers in that fields. Numbers are equal to the binary value of inputs. So this is 0, 1, 2, and 3. 4, 5, 6 and 7, 8, 9, 10 and 11, 12, 13, 14 and 15. Now we have to group all those positive states of ones. The bigger those group of ones are, the easier it is to build the logic device. So this is the one group, the second and the third. As you see, those two unknown states are treated as ones in our example. Our logicand function can be presented as this group, so this is AB, plus this group, small, so this is negative A, negative B, and negative D, plus this big group, so this is C. This is our logical device of that more complex example. As we see, it is made with 2 gates AND and 1 gate OR, according to that equation.
In this part, we'll talk about one of the most important branches in electronics: integrated digital circuits. So far we have discussed logic gates and we got to know simple layouts created from such gates. These were basic functional blocks. If you wanted to design a robot, it would turn out that you need so many gates, multiplexers and triggers that it would make your machine large and inefficient. As you remember, operational amplifiers perform arithmetic operations and comparators perform logic operations. Microprocessors are state machines that perform actions to retrieve orders from memory, decode them and execute them. Orders are elementary activities like operations on data or making decisions based on program's history. Data may be either values or addresses of information storage in memory. A microprocessor receives information about what to do and it downloads from memory data on which it will work. After order execution, you get the result. Processor commands are as simple as possible. Adding or moving a bit can be done in a single approach. However, mathematical calculations must be done step by step, taking into consideration the sequence of actions. This is because such systems use only logic states and interpret arithmetic operations using binary operations. Memory is a system which stores data. Usually, information can be saved, read, or overwrote unless you deal with a type of memory that can only be written once. Memory is divided into 2 groups: volatile and non-volatile. Volatile memory, also called RAM or cache, erases all stored data when the power source is turned off. Non-volatile memory, known as ROM or flash, stores data permanently. Another difference is that non-volatile memory is cheaper but also slower than volatile memory. For the same price, you can either have a fast RAM with low capacity or slow flash with high capacity. To sum up, storing data requires non-volatile memory and performing operations and calculations requires fast, volatile memory.
In previous classes, we have learned about basic electrical quantities, such as voltage and current. And we have learned also about the elements that can influence them. We have learned also that there are elements that can influence data, presented in bits. One can say that digital and analog are completely different words, and it's hard to combine them. That's why we have converters. Analog to digital converters, ADCs, convert the value of voltage or current, such as 2 volts, into corresponding digital signal represented by bytes. DACs, so digital to analog converters, convert the digital signal into voltages. Reference voltage is the maximum voltage in each converter system. In DAC converters, it is the maximum voltage that can be received on the output when we put the maximum bit value to the input. And in ADC converters, this is the maximum voltage that can be put to the input to receive the maximum bit value. Exceeding the value of the voltage reference may cause damage to the system, but sometimes we have to measure the voltages that are exceeding our range, or they are so low that we cannot optimally use the range of our converter. Then, it is important to condition the signal. There are many different treatments that allow our signal match the expectations of the converter. For example, when we have 7 volts signal and the maximum value of our input in converter is 5 volts, we can use the voltage divider made of 2 resistors, for example 30 and 75 kilo ohms each. Resolution. This is with how many bits we can represent our voltage. For example, 8-bit converter has 256 states because 2 to the power of 8 is 256. So now let's suppose that we have 10-bit converter and the reference value of 5 volts. Each step value is around 4.88 millivolts. So for example, if we have 0 on data, that means we have 0 voltage. If we have 512, it means that we have 2.5 volts. Changing values in DACs and ADCs is not very fast and it's slower than the normal operating time of our digital or analog device. The time of changing those values is called conversion time. It is often that high-resolution converters are much slower. But sometimes we have to compromise how quick we want to convert the data and how accurate the data has to be. However, technology is still developing, so there are more and more converters that have high resolution and they are very quick, but they are also very expensive. Okay, now we will learn how converters work. Here we have a voltage characteristic. We see that the voltage have different value in every time moment. So how to change that voltage into the digital number or digital number into that voltage? Our minimum voltage is 0 volts and the maximum voltage is 5 volts. We have 4-bit converter, so it has around 16 different states. So every state, every byte can represent 5 divided by 16 volts. So it is around 0.3125 volts. So if we have the number 0001, digital number, it means it is 0.3125 volts. And if we have 0010, it means we have 0.625 volts. Processors, memories, converters are systems that mixed together can create a very developmental device. If we planned and designed everything properly, we could create a system that without changing its mechanical structure could, depending on what is stored in the memory, perform various operations. We could program such a system and perform different functions every time. Nowadays, we do not need to construct such a system ourselves. Those integrated circuits are called microcontrollers. They are a complete set of microprocessor system offered with a large set of peripherals. It is probably the largest family of digital integrated circuits. Even 15 years ago, such systems were very poor, had little memory and their computing power left much to be desired. Today, for an affordable price, we can get microcontrollers, which are very fast, have a lot of memory, and they have a lot of good quantity peripherals. Now we have entered the journey of electronic components, laws of physics and electronics. In the next episode, we will learn something in practice. We will learn how to work safety, how to handle all the tools used in workshops, and we will start to project our own first electronic devices.